So today we will talk about Chapter 4, Section 3, Fundamental Theory of Calculus. In the previous two sections, we talk about the area under the curve fx, and especially the curve is positive, then we can form in this region, right? And also we defined the definite integral. We define the definite integral. We define the definite integral is from a to b ft here. By the way, here they use the letter t to denote the independent variable. It doesn't matter, right? It doesn't matter we use t or x. So the definite integral from a to b ft dt, which means the area under the function f from a to b, right? And we know this definite integral is the area, right? This one is the area, and it gives a number, right? A number, either positive or negative. If it's positive, that above the x-axis. If it's negative, that below the x-axis. Here is the t-axis. It doesn't matter. Okay, it doesn't matter. So here we use t. We use t as an independent variable in the function f. Now let's check. If we shifting, okay, if we cut some area like this one, if we decided the value between a and b, this one is x, and of course this x can shifting between a and b, then we can form some area. We can form some area from a to x, right? From a to x. Then how can we represent this area? How can we represent this area? You cannot hear appropriate? How about the other people? Can you hear me in a clear way? I think my voice should be good. So here, how can we represent the area from a to x under the curve t? So this one, this shaded blue region should be a to x. And what is the function? What is the function? ft dt. Okay, some people replied it's clear. Okay, my voice is clear. So let's focus on the topic. Okay, let's focus on the topic. So from here, how can we represent this area? How can we represent this one? Now it's the independent variable is t. How about my voice now? I use the ear plug. Maybe something wrong with the microphone. So here we use the independent variable t. Okay, we use the independent variable t. Now my x is the variable between a and b, and this x can be changed. Okay, can shift in the x from a to b. We can shift in the x from a to b. Now how can we represent this area? I'm just repeating this thing. How can we represent it? So this area is from a to x ft dt. Here in my definite integral notation, the independent variable becomes t. Now what is x? X is some value between a and b, right? Between a and b. So it can be this one. This definite integral represents the area. And here we know that x can shift in, okay? X can shift in. So we can have one more. Let me just repeat the graph again. The independent variable is t, y, and then this curve, okay, from a to b, and I can shift my x, okay? I can shift my x between a and b. So my x can be some value here. So this the area of this region. The area of this region, and this function we know is ft. So that is what I mean. We can shift the x. We can shift the x between a and b. Okay, we can shift the x between a and b. So this definite integral represents the area from a to x. Okay, from a to x. What is the x? X here is a variable actually, right? X is a variable, and as the x change, the area will change, right? For example, here I mark it as x1. So which one is larger? Which one is larger? Those two graphs, which area is larger? The first one or the second one? Of course, the first one, the area is greater than the second one, right? This is a to x1 here, a smaller one. This is a to x, which is the larger one. Make sense? So that is the area we are going to talk about here, okay? And we understand that the x, okay, the area will change as x shifting the value from a to b, right? From a to b. So actually this definite integral is a function of x, okay? It's a function of x. So be careful, okay? Be careful. Don't be confused with this notation and this notation in the previous sections. This is the definite integral. The lower and upper bound, they are fixed. But in this definite integral, the upper bound x is a variable. As the x shifting from a to b, the area will be different, right? Actually, we can define this one as a function gx, right? For example, when x equals x1, when we take the value x1, then that is the area. Or you can have your x2. Let me just use a different color, okay? Then you can have your x2 here, right? So your gx2 represents the area from a to x2 ft dt, the shaded blue part, right? The shaded blue part. And a to x1 is the shaded red part. This is the gx1, right? And of course, gx2, the function value at gx2 is greater than the function at x1. Make sense? So that is from a to x2. Then we understand actually this notation, this definite integral is the function of x, and we just call it gx. Okay, we just call this function gx. What does gx mean? Gx means the area, right? Gx means the area from a to x under the function ft. So be careful. What is the function f? What is the function t? This is the function curve f, right? We are talking about the area under the function f. What does g mean? Gx means the area from a to x. The x becomes an upper bound in the definite integral, so g is the function of the x. Make sense? Now we are going to check how can we find the gx at some specific value, okay? At some specific value. So for this notation, that is my gx with the upper bound x in the definite integral. So of course, first, the f is a continuous function. Okay, f is a continuous function on AB. X varies between a and b. When we call the function is integrable on the interval,
we said the function either should be continuous or has a finite jump of discontinuities. But here we should require, because the x was shifting anywhere between a and b, so we require the function should be continuous on the closed interval ab, and x varies between a and b. That's why we form the function, right? We form the function. So here, gx depends only on x, okay? Gx depends only on x. Gx depends on only x, which means g is a function of x with the independent variable x, and we know from the graph, gx means the area from a to x, right? And the variable x goes to the upper limit in the integral, right? And by the way, if the x is a fixed number, which means if we take the x value, for example, x1 or x2, if we give a specific value for the x, of course, if this one, the upper bound becomes a specific value, this becomes a definite value, right? This is a definite integral that gives a number. What does this number mean? This number is the area, right? Is the area under the function ft from a to the fixed value upper bound. Make sense? So in that way, the function value can be figured out. Of course, if you give a specific value for x, the function g is decided, the value is decided, right? So we let the x vary, we let the x change, then this number will also change. Of course, this definite integral will change as x change, and it defines as a function or about x, and we denote it by gx. Okay, so again, try to be clear about what is the function f and what is the function g we defined in this section. This is a function f, but we use another independent variable t. Okay, this is under the curve f. We're talking about the area under this function, and this is the new function we define here. And we discussed that this function g depends on the x. And what is x? X becomes the upper bound of the definite integral. Now we are going to look at the examples. Okay, we are going to look at the example to work out some function g values. So example 1, f is missing. If f is a function, of course we use t. Okay, the reason we choose t is trying to avoid the confusion between the x upper bound and the independent variable here. So we use a different letter t. That's the reason. If ft is a function whose graph is showing like this one, okay, like this one, and we define the gx is the definite integral from 0 to x, okay, from 0 to x, ft dt. Find the value of the function g at 0, 1, 2, 3, 4, and then sketch a rough graph for function g. Now, let's look at the function ft, okay, ft, this is t, the independent variable. So, of course, ft is defined from 0 to 5, right? So of course, f is continuous, no problem, right? F is continuous on the closed interval. ft is continuous on the closed interval 0 to 5. And here, we just use the graph. We don't know the function expression. We don't know the specific function. Okay, we just use the graph to figure out the function value g. So gx, what does gx mean as we defined before? So gx means the area under the f from 0 to x. Now, what are the x value I'm going to choose? I'm going to choose my x equals, so my x, I let my x equals 0, equals 1, equals 2, equals 3, equals 4, equals 5. And we need to figure out what is g0. By the way, what does g0 mean? G0 means when x equal to 0, right?
when x equal to 0. So according to the definition, actually it's 0 to 0 ft dt. This is one property we discussed. From a to a, what is the answer for the definite integral? In the graph, from a to a, it just forms a line. There is no area formed. Of course, the answer is 0. It's special case, right? It's special case from 0, 0. For example, yes, it's 0. For example, what does G3 mean when x equals 3? When x equals 3, what does G3 mean? Yes, it's 0. What does G3 mean? G3 means from, according to the definition, from 0 to x. So my x is 3, ft dt. Right? What does this notation mean? It's a definite integral, of course, right? With the fixed lower and upper limit, right? Now the upper limit is fixed with the number 3. So this one just means you find the area under the curve f from 0 to 3. Make sense? So now did you understand what are those G0, G1, G2, G3, G4 mean? Find the area under the function f from 0 to x. Now my x take all those values, right? So it's pretty easy actually. For example, what is G1? G1 from this graph. Let's look at it. Now we already figured out G0 is 0. Now what is G1? According to the definition, it's from 0 to 1 ft dt, right? So what is the area? What is the area they are talking about? From 0 to 1, and it's a triangle actually, right? That means we find the area of the triangle. What is the area of this triangle? This length is 1. How about this length? This length is 2. 1 times 2 times 1/2. Then G1 should be 0.5. How can you get 0.5? The area of this triangle. It's under the F from 0 to 1, right? From 0 to 1. That is the part I shaded, right? This is the area I shaded from 0 to 1, right? I use the red color here. So should be 1 times 2 divided by 2, right? So that is 1, right? The answer is 1. Now how can we find G2? G2 means 0 to 2, right? 0 to 2, ft dt. So that will be the area from 0 to 2, okay? Be careful. Here is 0 to 2, okay? The lower bound x is fixed in the function g. Here, let's check. In the function g, the lower bound is 0. So that will be 1 plus what is the area of this rectangle? What is the area of the second rectangle? This is 2, this is 1, so we get 2, right? We get 2. 1 plus 2, of course, the answer is 3, right? Now let's check the answers, okay? Let's check the answers one by one. So we already analyzed the function values, and we already analyzed from 0 to 1, 0 to 2, right? And we can do 0 to 3. Let's check it one by one. So that is G1, right? That is G1, the triangle. As I said, it's 1, this length is 1, this longer side is 2, so the area of the triangle is 1. And what does G1 mean? Now try to understand this function's notation. It's a definite integral from 0 to 1 ft dt, right?
Now G2 is the definite integral from 0 to 2 ft dt, right? Under the curve from 0 to 2. The first one, the triangle is 1. The second rectangle, the area is 2. Of course, then it's 3. Actually, you can also understand this one as the accumulated area. Okay, accumulated area. So here, this in yellow color, this rectangle, this is 1, this is 2. So the rectangle area is 2, so should be the triangle area 1 plus the rectangle's area, right? So G2 actually, G2, we will go through one by one, okay? We will go through one by one. So G2 actually is the accumulated area from 0 to 1 and 1 to 2, right? How can we understand that this is 1 plus 2? Because G2 is when the upper bound is 2, ft dt, right? How can we write it as 1 plus 2? What is 1? 1 is the area from 0 to 1, ft dt. What is the 2? 2 means the rectangle area. What is the rectangle area? That is from 1 to 2. Also, you can understand this is the accumulated area from 0 to 2. And this is a rule, right? 0 to 2 equals 0 to 1 plus 1 to 2. Make sense? So that is the first part. The first part is 1. Yes, someone replied as Damu. It's perfect. Yes, it's perfect. Now, the third one, okay? The third one. Here we estimated this one. We estimated this part from 2 to 3. It's greater than triangle, of course, this part, right? This part is greater than triangle. So we estimate this one from 2 to 3. FTDT is 1.3, okay? 1.3. We estimate, okay? We estimate this part is 1.3. Of course, it should be greater than 1, right? Should be greater than 1. It's a little larger than the triangle. So I use the purple color to denote that. Now G3 means, according to the definition of the function gx, G3 means 0 to 3 ft dt, right? 0 to 3 ft dt. You follow this rule, you can write it as 0 to 2 plus 2 to 3, right? 0 to 2, 2 plus 3, 2 to 3. 0 to 2 plus 2 to 3. 0 to 2 is 3. And we estimate 2 to 3 is 1.3. So that's why the accumulated area from 0 to 3, we get G3 is approximately 4.3. Okay, and you will notice that all those gives a positive number because all those areas are above the t-axis, right? Are above the horizontal axis. That is G3. Now let's check G4. Okay, let's check G4. So G4, according to the curve, okay, according to the given curve of FT, this is G4. Now we understand that this part is the manners with the area, right? It's a manners. Let me just choose this kind of color. So here we already know G3, this part is 4.3. Now actually this part from 3 to 4, FTDT, it's symmetric about this part. They are symmetric. Okay, they are symmetric. So we can estimate this one is also 1.3, but since it's below the horizontal axis, the area should be minus sign. Okay, the area should be minus sign. So the area from 3 to 4 is minus 1.3. So again, G4, Okay, we can write G4 according to the rule. G4 equals 0 to 3 ft dt plus 3 to 4, right? According to the additivity rule, 3 to 4 ft dt. 0 to 3 we know it's 4.3. Now 3 to 4 is minus 1.3. Here is plus the area, but the area is a negative number. So of course this is approximately 3 because this part we did approximation, this part. Okay. How is 1.3? Just estimate it. Okay, with the estimation, it's given. Okay, it's given. But anyway, you know it's greater than 1, right? It's greater than 1. We are not going to check how we get it. Okay, how we get it. We just give approximate number. You can call it 1.2. It's no problem in this question. Okay, you can approximate by 1.2, but if you approximate by 0.5, 0.7, then it's wrong. Okay, it should be greater than 1. Now G5. Okay, G5. I think the miss one more question should be when x equals 0 until 5. Okay, we miss one more question. So what is G5? So here actually this is 1.3 minus 1.3 again because it's symmetric from 4 to 5. Okay, from 4 to 5. So the area from 4 to 5 ft dt, the definite integral from 0 to 4 to 5, it's also minus 1.7. Okay, minus 1.7. So this G5 equals this is equal the definite integral from 0 to 4 plus 4 to 5, right? And from 0 to 4 we approximately get 3, and actually this part is G4. G4 plus 4.5 is minus 1.3. So it's 3 minus 1.3. That's why we get 1.7. Okay. So this is 1.7 and the G5 actually this one is the net area, right? Net area. The number is not is the positive one with approximately 1.7 net area. Okay, net area. It's showing here, right? Plus the it's above the horizontal axis, it's plus sign. It's below the horizontal axis, it's minus. Okay, it's a negative sign. So here we can understand the way we define the gx, that actually is the accumulated area we did, right? And by the way, can this x goes to 6, 8? Of course not, because the function, okay, the function f is on the closed interval 0 to 5, right? So the x value we can choose in the function g. Here, my function g, the x we can choose is between a and b, right? Between a and b. Sorry, between 0 and 5, right? Between a and b. Let me just write a and b. And we understand the function g is the accumulated area from a to x, right? From a to x. Now let's check the rough graph of g. We get several values for g, right? Like g0 is 0, g1 is 1, g2 is 3, and g3 is 4.3, g4 is 3, G5 is 1.7, right? Then with those values, we can get a rough graph for function g. We can get a rough graph for function g. This is just a rough graph. What are all those values we have? Let me just list as a table. Okay, let me just list as a table. How can we draw some rough graph with the given values? Come back to red color again. So here we have some x values, 0, 1, 2, 3, 4, 5. And what are all those gx values? When x is 0, this is 0 because that's a definite integral from 0 to 0. When x is 1, that is the triangle's area, which is 1. And when x is 2, that is triangle plus it's from 0 to 2, that's triangle plus rectangle, we get 3. And when x is 3, 4.3. And what is this one? 3 again, right? 1.7. So with this table, we can get a rough graph for G. Okay, we can get the rough graph of G. And what is my function G again? G is defined in this way. The x, okay, the independent variable x is the upper limit of the definite integral, right? It denotes the area under the function f from a to x, okay, from a to x. So some people said happy birthday to someone. I think you can do it during the break, okay? Our demo is just a comment about my lecture. It's not an advertisement, okay? So that is the example one we are talking about. If f is the function whose graph is shown and the gx is defined in this way, so we can find all those values. Then sketch the rough graph. We did it. Okay, we did it. So that is example one. Now let's check what is fundamental theory of calculus. Okay, we are trying to understand this function g. So if f is continuous on AB, if function f is continuous on the closed interval AB, then the function g defined by this way. Of course, x is between a and b, right? As I said, because the function f is defined on closed interval AB. X is just the shifting. Think about the graph at the very beginning. X is shifting between A and B. So this function G is also continuous on AB. Is also continuous on AB and differentiable on the open interval AB. And the important thing between G and F, you might ask, what is the relation between the function g and f if we define the function g in this way? The derivative of g equals the function f with the independent variable x. This implies the connection between g and f. So the derivative of g, that means you just change this function ft into fx. Understand? So it's easy, okay? If we have function g defined in this way, then the derivative of g, that just gives the fx, okay? It's differentiable, and the derivative is fx. So part one gives the derivative of g in a direct way, okay? In a direct way. Also, that reveals the connection between f and g. Make sense? Now I think it's almost time. Let's take a break. Then we are going to look at the several examples based on the fundamental theory of calculus 1.